HIDA lecture today. We are very happy to welcome you here at our, virtually at our HIDA premises in Berlin. I think we will wait a couple of minutes because still people are coming in here. So just give us a second so that everyone can join. So great, we are getting started now. So welcome everyone to our HIDA lecture today here in Berlin. We're very happy to have you here with us. I will give a short introduction about the Helmholtz Information and Data Science School. We at HIDA are part of the Helmholtz Association, and Helmholtz is Germany's largest scientific organization with 18 research centers and 6 research areas. The Helmholtz Information and Data Science Academy connects and serves as a roof of 6 data science research schools throughout Germany. And my colleague, she will post a couple of links soon in the chat, so you will find a little bit more information about our research schools and also about HIDA. So with that, HIDA is Germany's largest postgraduate training network in information and data science throughout Germany. What we offer here at HIDA is exchange and visiting programs. We offer training and networking events, and we share a data science job site at our website, where you can find all job offers throughout the Helmholtz Association in the field of information and data science. So yeah, just subscribe to our newsletter, check our website for more information. And with that said, I would like to welcome here with us today Itzik Klein and ask him to come on the stage. A very warm welcome here to us in Berlin. Itzik Klein is visiting us from Israel, and he is associate professor at the HIDA Department of Marine Technology at the Cherny School of Marine Science, and as well at the Autonomous Navigation and Sensor Fusion Lab at the University of Haifa in Israel. And the University of Haifa in Israel is part of our the Israeli Data Science Initiative. And with this network, HIDA set up a partnership, and we are hosting events together. We are sharing information and hopefully also intensifying the connection between the researchers of our countries. So I'm very happy to have you here with us today, Itzik, and the floor is yours. And
Thank you very much.
Please tell us more about your research.
Great, thank you very much. Let me share my screen. Okay, so hi everyone. Thank you, Victor, again for your kind introduction. Good morning. I'm happy to be here. And before I start my talk, I just wanted to say that if you guys have questions, you can feel free to stop me and ask. I won't be viewing the chat only until the end of my talk, so you can feel free to interrupt and if there are questions. So today I'll talk about data-driven inertial sensing. Usually there is a confusion between navigation and guidance, because if we open a dictionary, it will be determining or planning of a naval vessel or aircraft position and course. For example, if we are in point A and we want to arrive to point B, and we are asking ourselves what will be the best route to take, this science is called guidance. We want to design a path from point A to point B. It could be the shortest path, it could be the interesting one, and so on and so forth. And navigation, what we want to do is to determine the position. What is our position relative to the world? And today we'll be focused only on navigation. Then actually navigations aim to answer three questions. What is our position, velocity, and how we are oriented relative to the world? If we have this solution, then we have what is known as the navigation solution. And generally, we have two approaches how to perform navigation. One is called position fixing, and the other is called dead reckoning. In position fixing, we receive measurements from sensors, and we determine our point in a single point calculation fashion. That is, there is no correlation between the point. Its point relates on different measurements. For example, the global navigation satellite system is one system that we can calculate each point separately. On the other hand, in the dead reckoning approach, what we generally do is we integrate velocity or acceleration measurements in order to determine the position. And since we are integrating velocity or acceleration, then the position points are related and connected to each other, as can be seen here by this arrow, for example. One of the popular systems acting on the dead reckoning principle is the inertial navigation system. I will talk a little bit about GNSS, the Global Navigation Satellite System, and then I'll move forward to inertial navigation system. By the way, I haven't mentioned yet, this is kind of a short introduction into the navigation field, and then I will be more focused on what we did in data-driven approaches within the navigation framework. So a little bit about the GNSS, which I'm sure most of you are familiar with. But in general, we have satellites flying, orbiting the Earth. They transmit signals. We have receivers on the Earth. For example, like we have on our smartphones, the receivers collect the data and is able to calculate our position. In generally, more GNSS satellites will be available, the better will be the accuracy and the robustness. The accuracy is about several meters, and if we are working with precise RTK calculation, then we can reach even an order of magnitude. You can see here below several types of satellite constellation orbiting the Earth. We have the Baidu, the GPS, the GLONASS, and the Galileo, and of course there are also a regional satellite system, but the principles are the same. We collect the data from the satellites, the RF signals, and we calculate the position of the receiver. So usually when we are working, with a receiver in the open sky, there should be no problem, and the accuracy and robustness are quite fine. However, in some environments, like in urban environments, there could be a line of sight blockage, and there could be a result of a multipass of the signals, which greatly degrades the performance of the GPS, so sometimes even to tens of meters. In other environments, like in underwater or indoors or underground, the GNSS signals are not available. Therefore, GNSS cannot be used within those environments. On the other hand, an inertial navigation system is a system that works everywhere, regardless of the environment type. It works in space, it works on Earth, underground, land vehicles, and every other environment you can imagine. It has its own systems. It has its own sensors. It has two types of sensors, actually. One is the accelerometer, and the other is a gyroscope. For those of you who are not familiar, accelerometer is a device that measures a creature called a specific force. Let's address it as the acceleration without the gravity. And gyroscopes measure the angular velocity of the body. So we have three orthogonal accelerometers and three orthogonal gyroscopes arranged in a system known as inertial measurement unit. The output of the gyroscope is then integrated to calculate the navigation solution, which is the orientation, the velocity, and the position. You can see here typical inertial sensors, how they look and the relative size. We all have inertial sensors embedded in our smartphones, and they are used continuously in lots of applications. By the way, the first usage for the accelerometers was to identify that the position of the smartphone is changing from vertical to horizontal. And this system is called the inertial navigation system. It takes those measurements of the inertial sensors, integrate them, and provide us the inertial navigation solution. The main disadvantage of those sensors is that since we integrate raw data, the raw data contains noises and biases. And therefore, when integrated, it causes a solution drift, as can be seen here in this illustrative example. For example, if we have an offset known as a bias in the accelerometer measurement, when integrated once, it will result in a linear error over time. And when integrated twice, it will result in an error as a function of the bias value and the time since the beginning of the journey. So this is the main disadvantage of the inertial navigation system. You can see here to the left a lot of applications that uses inertial navigation. And in order to stop or mitigate the solution drift, usually what we do is we use a navigation filter. In the navigation filter, we use the building blocks of the inertial navigation system, as I showed you in the previous slides. And we are utilizing external data like GNSS measurements, Doppler Velocity Log, which is a device used at sea. I will talk about it later. Some also zero velocity updates indoors and many types of different sensors. Fusing them together in the navigation filter helps us to mitigate and even to circumvent the solution drift of the inertial navigation system. So in general, this is I call it the big inertial circle because it has all the building blocks of the navigation related issues or topics. First of all, the first and basic building block is the inertial sensor. This is the accelerometer or gyroscope. And when we are arranging 3 orthogonal accelerometers and 3 orthogonal gyroscope in a device, as can be seen here to the right, we have what is known as the IMU, the inertial measurement unit. It also contains sometimes a temperature sensor in order to calibrate the sensor as a function of the temperature and some software algorithms. Then if we take those accelerometers and gyroscope and combine them together with magnetometers, we can calculate the heading and altitude of our platform, which is how we are oriented relative to the world. Magnetometer is a device that measures the magnetic field, and together there are algorithms that enable to obtain the orientation. It is called altitude and heading reference system. The inertial navigation system contains all those sensors, specifically the accelerometers and gyroscope. And as I mentioned earlier, it helps us to calculate the inertial navigation solution. Finally, the navigation filter contains the INS and also measurements from external sensors in order to mitigate the navigation solution drift. Until recently, all of those systems, all of those models, all of those algorithms are model-based. And what we are doing is we are working in the interaction between the artificial intelligence world and this navigation world and provide algorithms that employ the benefits of artificial intelligence, as I will soon show you. By we, this is, my team lab. You can see here we have a team of 20 students. Seven of them are PhD students. We have 2 researchers, 1 lab engineer, and I'm trying not to get in their way. The lab was founded 2 years ago. We are addressing all types of navigation-related issues, starting from sensors through HRS and INS algorithms, nonlinear estimation, external sensors like GNSS or DVL, and mainly AI algorithms. This work is done for various types of platforms like vehicles, robots, humans, animals, and also medical devices. You can see here below our department 2 types of autonomous underwater vehicles. I will soon talk about one of them. We have also mobile robots, quadrotors, and different types of inertial sensors, including inertial sensors arise, and many more things that we play with. So, of course, we do also classical, traditional model-based learning and not learning, research. But we mainly are focused in data-driven research, as you can see here in the top view diagram, that I made it as a function of our, I divided our work as a function of the platform type. And this is all the stuff that we published in the last 2 years. This is a multi-purpose navigation and fusion. That is, all those works are suitable for any type of inertial sensors and for any platforms. We have here works addressing anomaly detection, noise reduction, altitude and heading reference system, and also nonlinear filtering. We have also some research that are tailored to specific platform, for example, autonomous underwater vehicles, quadrotors. We have also a task of an autonomous dozer with a grading task. This is a joint research with Bosch. They have a center in Israel, an artificial intelligence center. And we also did some work on mobile robots. We did also several works on detecting ataxia dogs. Pedestrian dead reckoning is an approach for indoor navigation using a smartphone. I will talk about it later on. And we also collected several data sets. Of course, this is a lot of work that we've done. I don't have time to review all of them, so I'll review just a little bit of them. And all the information is publicly available. And if you have questions of one of the topics that I'm not talking here today, you can please feel free and contact me later on. So as you know, there is a difference between artificial intelligence, deep learning, and machine learning, although sometimes those people that are not familiar use the same, one of the three interchangeably to mean the same thing. However, of course, there is a difference. In artificial intelligence, is actually the field of creating intelligent machine. Machine learning is a subset of artificial intelligence, and there we want to make machine learn from data without being explicitly programmed to. Specifically, we are using expert knowledge to derive and extract features, and using those features in machine learning algorithms, we can perform our task. Deep learning is a subset of machine learning that instead of creating handcraft features by experts, the network itself learns the features and helps us to perform our task. So I will talk a little bit about machine learning algorithms that we work with and a little bit about deep learning algorithms that we work with also. Regardless of the learning strategy that we tackle, we usually refer to the learning approach that we tackle. So we usually refer to two types of learning strategies. The first is an end-to-end learning strategy. In this strategy, what we do is we want our learning algorithm to learn all the steps between the input and our desired results without relying on any model-based information. On the other hand, in the hybrid learning strategy, we take the model-based approach and we replace only a subset of the step with the learning algorithms. And this is a combination between the model-based and the learning. It's called a hybrid learning strategy. So we are working with both end-to-end and hybrid learning strategy. As you are familiar, I assume that an end-to-end learning strategy is like a black box. You know what you input and you hope to receive the results that you desired. And in a hybrid approach, we are relying on well-calibrated model-based equations and theory. So we work with both types of strategies depending on the problem at hand. Of course, in order to work with machine learning or deep learning in either strategy, we need a lot of data. And data is the most challenging part of developing a machine learning-based algorithm, because data is very hard to collect and it's sometimes very challenging also. In the navigation field, a lot of data is lacking. You know, for example, in the computer vision field, there is a lot of available data sets, and people that are working in the field go to the GitHub or other places, take the data set and they can work with. But in the navigation field, there is not enough data sets. So one of our initial work was to collect the data set you can see here from various platforms like quadrotors, different types of mobile rotors, ships, two types of AUV, land vehicle, and some more platforms. We are currently doing another set of recordings. And by the way, this is why sometimes machine learning approaches are known as data-driven approaches, because we need data in order to work with those approaches. So until now, it was a short introduction to navigation. And now I'll talk specifically of several works that we did. I will start with autonomous underwater vehicle navigation. So first of all, AUVs, autonomous underwater vehicles, are used for a variety of missions. You can see here, for example, environmental missions, ocean mining, science, military missions, and many, many more. Usually, a typical AUV will have two types of sensors: inertial navigation system, which I discussed recently, and a device known as Doppler Velocity Log. A Doppler Velocity Log, you can see here, by the way, this is a real teledyne Doppler Velocity Log mounted on our AUV. This Doppler Velocity Log transmits 4 acoustic beams to the seabed. The beams are reflected back, and utilizing the Doppler effect, we can calculate the beam velocities. If we have enough beam velocities, which is 3 or 4, then we can calculate and estimate the AUV velocity vector. So this is a very simplified least square algorithm, a model-based least square algorithm that takes the measured beam velocities, the directions of the beams, and able to calculate the AUV velocity in a Cartesian frame that the navigation filter uses later on. And what we did, a work led by Nadav Cohen, is that we designed 2 types of algorithms that we call BIMSnet 1 and 2 in order to learn the velocity of the AUV given the DVL measurements. So what we did, the first algorithm utilizes, besides the DVL measurements, it utilizes also the inertial sensor data. And you can see here a diagram of our proposed approach. Actually, it's an end-to-end network. We deliver in the input the inertial sensor data, and along the way, we also deliver the DVL measurements. So the IMU data are used in a different, actually it's a multi-HID architecture. So first we have to extract the features from the inertial sensors. We use the current DVL measurements, plug them together into a regression network, and then we obtain the velocity solution. You can see here below the network architecture. It's not a very dense network. It's mainly based on the 1D convolutional neural network, and it's able to provide a velocity solution. But in order to apply this approach, we need to have an inertial sensor raw data. Since in some cases, only a DVL is present and we don't have inertial data, we propose what we call BIMSnet 2 architecture. There, what we do is we take n past DVL measurements for the feature extraction phase, combine them with the current DVL measurement into a different regression network. You can see here the architecture of the network here is much shallower than the previous one, but the result is the same. We want to obtain the velocity vector. So in order to estimate and see if our approaches are working and how good are they compared to the model-based approaches, we conducted several experiments. I will show you a video. Hope it will work. Just a second. Okay. So this is our AUV. This is the, we call it Snappir. It's an ECA Robotics A18D AUV. It's 5.5 meter long. It is, sorry for the low-tech smartphone video. This is a much more high-tech recording. It's a 5.5 meter long AUV, capable of 24 hours working autonomously with a maximum operational depth of 3,000 meters. What we did is we collected raw data for about 4.5 hours. You can see the sampling rate of the inertial sensors and the DVL. And the recordings were made in different dynamics, as you can see here, actually 9 different missions with different parameters. So first of all, what we did is we wanted to answer the question, how many past measurements for the DVL do we need for our BIMSnet second architecture? So we use the RMSE, the root mean square error of the DVL as a function of the past measurements. And you can see here we obtained a minimum at 3 past measurements. So we used 3 past measurements in our algorithms. And here are the results on the test data set. We obtained those numbers for the RMSE. And what is important to note is that we improved the model-based by more than 54%. We think that the reason for that is that we leverage from the network capabilities to reduce noise and also to handle non-linearities in the data. So this is a very nice improvement compared to the model-based approaches. Next, we address the case of partial DVL measurements. In order to obtain the velocity measurement, we need at least three DVL beam measurements, and the fourth one is for redundancy, but it greatly improves the accuracy of the solution. So if we have one or two beams, we cannot calculate the AUV velocity vector. In real-world scenarios, sometimes this is a situation that happens, that we have one or two beams available due to the reason that you can see over here. So this is actually the difference between theory and practice. So in practice, we don't have 4 beams, we sometimes have 2 or 1. And actually, this is quite important. For example, if there is some short time period that we don't have a DVL solution, DVL is the main sensor, the main navigation sensor of the AUV, then the AUV will have to stop its mission and to surface. So therefore, this is not a desired situation we want to be in. So in general, if we are in this situation, and as I mentioned before, we can't calculate the DVL velocity. So the navigation solution will rely only on the inertial sensors. And since those are integrated, the solution will drift. And this is a situation that we don't want to be in. Therefore, the AUV surface. So what we proposed is to use deep learning approaches in order to estimate the missing beams solution. Moriona led this work, and what we did here is similar end-to-end network with also a multi-head network. We extract the feature on the past DVL measurement, and we use the current measurement, but this time not for the velocity estimate, but to estimate the missing beams. We tried 2 different architectures. First, to regress all the beams and then take only the missing ones. And in the second architecture, what we tried is to regress only the missing beams. In contrast to the work I showed you by Nadav, more used LSTM network. Usually, from a theory point of view, LSTM, long short-term memory, is supposed to handle better time series data. However, in practice, there is a debate which one of the approaches is better. So we usually design an LSTM network, we design a CNN network, and we compare between the two. In some problems, CNN is better, in the others, as here, an LSTM approach provides better results. We use here a different data set. It is bigger this time. It contains 10 hours of recording, only DVL data with a sampling rate of 1 Hertz, same AUV. You can see here 3 types of trajectories that were made and the data collected during those trajectories. And you can see here the result. FR means a fully regression. That is, we are regressing all beams. No matter what beams are missing, we are regressing all the 4 beams and then taking from the 4 regressed beams, only the missing one. In CV, central beam, we are regressing directly only the missing beam. And you can see here from this diagram, we compared LSTM to the left and CNN to the right, that our LSTM architecture using CV, that is, we regress only the 2 missing beams, obtain the best performance. We tried all possibilities of 2 missing beams. This is, for example, beams 1 and 2 missing, and so on and so forth. We are giving here the statistics and results for our missing beam approach compared to 2 model-based approach. The first is a trivial, but the baseline approach that is used is taking the average of the past beams that are missing and using this average as a current beam. A virtual beam approach is under the assumption that there is no velocity to the right. And you can see here that regardless of the 2 beams that are missing, our deep learning methods perform much better than the model-based approaches. So in this type, we regress the missing beams and we are able to calculate the missing beams and to calculate the velocity vector. So this is our work on the underwater part. Now we are moving to indoor navigation. So why indoor navigation or localization is important? By the way, just for terminology, localization meaning that we are interested only in the position, and by navigation we're interested also in the position, velocity, and orientation. It's of course depending on the application at hand. So you can see here a list of motivation for the importance of indoor navigation, like of course navigation. We are arriving to an unfamiliar building like a university, hospital, or a mall, and we want to navigate and understand where we are relative to some point. Of course, there are some types of user services, security, and so on. GNSS signals, the satellite signals, do not penetrate indoor environments, therefore cannot be used. So there are other approaches how to use additional sensor to navigate. First of all, it's called magnetic field fingerprinting. We can use, what we do in this approach is we measure the magnetic field of the building before usage. And then while we're inside, we use magnetometers to do the matching. Vision approaches, we have also Wi-Fi and other RF signals that are used for localization only. And we have inertial sensors. Inertial sensors, as I mentioned before, are already mounted in our smartphone. Therefore, it's very easy to operate. When a user goes inside the building, he uses his smartphone in order to navigate. So we are focused only on the smartphone inertial sensors solution to do the indoor localization, indoor navigation approach. Okay. So one of the common approaches to do indoor navigation using inertial sensor is called PDR, Pedestrian Dead Reckoning. In general, it has 4 steps. First, we detect the user steps, like when I'm walking now, I'm stepping, and then we detect the step. We use empirical formulas, as you can see below, 2 types of empirical formulas. Some of them are based on biomedical approaches that estimate the step lengths that we traveled. We use the gyroscope to determine our heading, and then it is all combined given initial conditions in a PDR algorithm, which is a very simple model-based formula in order to propagate and estimate our current position. Those 2 approaches are known as the Kim approach and the Weinberg approach are used to determine the step lengths. As you can see, the Weinberg approach is a function of a gain and a function of the measured acceleration during the steps. And the same for Kim's approach is a function of a different gain and also the absolute value of the acceleration. This gain is very sensitive to the dynamics of the user. For example, if we are walking, if we are running, and if we are standing, and is what we showed that is also very sensitive to the smartphone location. For example, if we are texting with the smartphone or swing is a motion when the smartphone is held in the hand and we are walking like this, and talking, of course, and in the pocket. So you can see here in this figure, I'm showing you a normalized values of the acceleration magnitude doing different type of smartphone locations. So you can see there is a difference. And if we are designing again to work when the smartphone is in the texting mode, in practice we are in talking mode, the gain will be is not correct. It's inaccurate, and this will result in a large position error. So what we suggested is take the same PDR model-based methodology and just add one more building block, which is to detect the smartphone location. And we called it SLR, smartphone location recognition. Other approaches showed the same approach, only to identify the human activity, like running and walking and things like that. And we were focused on the smartphone location. So what we did, we designed a classification network, as you can see here, a very simple CNN network. You see the structure to the right. What it utilizes only the accelerometers and gyroscope reading that are already mounted on the smartphone. And using this network, what we show using a data set composed of 8 different data sets that are publicly available. You can see the names of the data set here. They consist of 107 people, 31 hours of recording. We managed to obtain very nice classification results on each of those data sets. Some of them were only provided in the test set and not in the train. All of them actually, all those 5, and all those 5 data sets. And this was 3 data sets were used both in train and test. And you can see here the accuracy. This is quite nice classification accuracy. We tried here 2 different types of network architecture, CNN and a combined CNN LSTM architecture. As you can see here, this is the last LSTM layer after the CNN layers give us the features. And the network is capable to providing the mode of the smartphone. We also showed that we need to use only accelerometers, and the results remain more or less the same. Next, what Nati Daniel proposed is to work with computer vision algorithms, because computer vision and deep learning was bloomed about 10 years ago, started to bloom, and there is a lot of algorithm, there is a lot of data. So Nati said, why not use this data? So what we did is we designed an encoder that takes the accelerometers and gyroscope readings and encode them into an RGB image, as you can see here. You can see here 4 types of images as a function of the smartphone location. And what we additionally did is we leveraged from ImageNet. ImageNet is a data set containing more than 1,000 labels of different titles. And we use transfer learning and also in our approach here. That is, we use the computer vision transfer learning to the navigation field. And we design a classification network in order to estimate the smartphone location. So we did this also. Here you can see the result of the classification for SLR, smartphone location recognition. The first 2 algorithms are the state of the art, and this is our result for the SLR. So you can see this first is the state of the art. What we did is elaborate this approach by adding also gyroscope readings, which obtain the best performance. And this is our approach using both accelerometers and gyroscopes for the SLR. But for the human activity recognition, we tested 4 different data sets. We performed better, and the overall accuracy of our approach was much better. That is, compared to our previous SLR approach, those results using 2D CNN and our encoder perform much better than a time series approach. Next, instead of just identifying the mode and plugging it into the model-based algorithm, we tried an end-to-end approach. In the end-to-end approach, what we do is we estimate the change of the distance and the change of the heading the pedestrian did between 2 successive steps. Omri Asraf led this work, and we designed a neural network based mainly on residual networks. And we use a publicly available dataset to verify our approach. You can see here the results. We tried a test in 3 different types of smartphone location: texting, pocket, and body. You can see here the trajectory lengths and the average and the STD. This is a PDR, is a traditional PDR, the model-based approach, optimized by the best parameters. You can see here the average performance. And this is Ronin. Ronin is the state-of-the-art approach. It does not use a classification approach to identify the smartphone mode. And this is our approach. So you can see that on average, we perform much better compared to Ronin. And we think that the reason that our approach performs better is that we use this SLR model before using directly the regression network. You can see here an example of the trajectories. Just keep in mind that since we are working with inertial sensors, regardless if we are using a model-based approach or a network, the solution eventually will drift in time. So therefore, those solutions are currently only for short time periods. We are working in order to make them work for longer durations. So we were underwater, next we were indoors, and now we are talking about attitude and heading reference systems. Actually, those algorithms are valid for any types of platform. And you can see here several applications of HRS, and I'm just reminding you that the goal of an HRS algorithm is to estimate the orientation of the platform. So they are used for gimbal control, antenna pointing, industrial robotics, instrument buoy. And what we are focused on is when we're holding a smartphone and we are wanted to play with augmented reality or virtual reality application, we need to do motion tracking of the smartphone. And we are focused on that problem. And just for those of you who are not familiar, I want to talk a little bit about the structure of an HRS algorithm. So in general, this structure takes the inertial sensors, the gyroscopes, and as the main building block. We use the attitude kinematic equation of the gyroscope to estimate the orientation. And then using fusion algorithms and accelerometers and magnetometer measurements, we correct the gyroscope's measurements and estimate better the attitude and heading. There are different types of model-based approaches like complementary filtering, Kalman filtering, extended and adaptive Kalman filtering, and the list goes on. What Eran did is, instead of using model-based approaches, we use a hybrid approach, as I will soon present you, and just reminding you that we are focused in pedestrian walking in an indoor environment. And the main challenges of the HRS algorithms is to cope with linear accelerations, as during walking, of course, we apply linear acceleration, and if we are in an indoor environment, most of the time there is a lot of magnetic interferences. So usually when there is magnetic interferences or linear accelerations, those algorithms do not perform well. And this was our challenge, to make them work well even under linear accelerations and magnetic interferences. So what we did here, you can see our hybrid approach block diagram over here. We use the same gyroscope kinematic equation as any model-based approach uses. And what we did, we designed a unique network that relates between the residual, which is the accelerometer measurements, minus the expected gravity. It relates between those residuals to the gain. The gain is used to update the external measurements of the accelerometer. So we design a network instead of using model-based approach. This is the network structure. We did input augmentation of the residuals. We also designed a soft threshold function to maintain the gain in the values between 0 to 1. And you can see in the table below our results for 4 different types of smartphone location: pocket, texting, body, and bag. You can see by overall, we approved the model-based Metric and Mahoney are the most popular complementary filtering HRS approaches. We also estimate an extended Kalman filter approach and an adaptive Kalman filter approach. This is another work that we did using a model-based optimization technique. And this is our approach that we use the deep learning in order to regress the gain. And you can see here that our approach improved by more of 40% the model-based approach and approximately 10% our previous work. And this HRS algorithm is suitable for any platform and like, Quadrotors, AUVs, people, and so on. What I'll talk now is a hybrid adaptive Kalman filtering. And this is also work that can be applied to any type of platforms. So first of all, a little bit teaser for those of you who are not familiar with Kalman filter. This is the Apollo mission, the Apollo model. And the legend says, or the storyteller says that Kalman, who invented the Kalman filter, presented his work in a conference, and one of the Apollo managers saw his work, and he dragged him into the Apollo program, and with his help, they implemented the Kalman filter, as you can see here, for the trajectory tracking. This is how the Kalman filter was related to Apollo, and the legend said that this is what enabled the successful missions of Apollo when they used the Kalman filter. So Kalman filter was invented around the 1960s, was used during all Apollo missions. And in general, it has 2 parts. It has a prediction part and it has a filtering part. In the prediction part, what we do is we use some sort of a dynamic model in order to predict the next step of the vehicle. And in the filtering part, we use external measurements in order to update our assumption. Since we are using a kinematic model, there is an uncertainty. And this uncertainty is reflected in this parameter known as the process noise covariance. Under the normal Kalman filter assumption, this parameter is kept constant. However, as the trajectory varies and the dynamic changes, the uncertainty is not constant. Therefore, for a long time, what people were suggesting is to use what is known as adaptive values for this process noise covariance to cope with the uncertainty. Recently, Professor Yaakov Bar Shalom, which is a distinguished professor and one of the experts in filtering, and in some of his co-authors, addressed this work known as a 50-year-old problem from a model-based perspective. And what we did is address this problem by a learning-based approach. And that is, by the way, who led this work is Barak Or, which recently completed his PhD. And what we suggest here is to take the aiding sensor NINS as taken in the model-based approach. We use the same equations as in the model-based EKF. Just instead of using a constant or an adaptive approach to estimate the uncertainty of the process noise covariance, we design a process noise regression network. So this is a hybrid approach relying on the well-known Kalman filter, and the extended Kalman filter means that the problem is not linear. If the problem is linear, we use a linear Kalman filter, and if the problem is not linear, we use an extended Kalman filter. Usually, the navigation filter consisting of a INS as a building block and an external sensor is a nonlinear problem, and therefore the extended Kalman filter is used. So what is nice in this work that we were able to design a simulation, a very simple simulation, consisting of 6 different baseline trajectories, which were used to create the trained data set. That is, unlike in the AUV situation, we didn't have to do a huge amount of recordings with the platform itself. Here we could rely on a simulative data set. So you can imagine it is much easier to rely on a simulation data for the training, and hopefully the testing will work, and I'll show you later on. So we used 6 trajectories to represent the actual trajectories. Then we added to them some sensor noise to reflect actual inertial sensor measurements. And this was used only, the simulation was used only as train. You can see here the network Barak suggested. It comprises of CNN network, CNN layers, sorry, and we use only the inertial data, the accelerometers and gyroscopes as input in order to regress the process noise value. So in order to validate the approach, we conducted a field experiment using a quadrotor. You can see here the Matrice RTK quadrotor. This is the type of the trajectory that we examined. And you can see here to the left our result. This is our result in the first line when we are examining the position mean absolute error and the position root mean square error. Those 3 are different types of adaptive filters in order to estimate the process noise, and those 3 are constant based. So you can see here our improvement, it's less than 10% from the model based. We currently have new results which perform them even better. But this approach using a neural network in order to estimate the gain, the process noise, sorry, was quite novel at the time, and currently we are continuing to work on that. One of the examples that we leverage from the deep learning approach, and instead of using a deep learning network to regress the uncertainty, what we did in our second work is we use handcraft features in order to estimate the uncertainty of the process noise. And you can see here what is nice that we use a two-step procedure for the feature extraction. We took the signal, we use 3 types of features that provide us different types of the signals, and then we calculate the actual features. We compare this approach to the DNN approach with the same network that I presented to you in the last slide, and to other adaptive filters and to model-based filters. And here we obtained a very nice improvement of the speed, root mean square error, and speed mean absolute error. Only simulation result in this time of an AUV with a DVL. Currently, we are working on the experiment results, and we hope that it will yield the same performance. So I think I still have time. So this is the last subject. This is specifically for quadrotors, and it's called quadrotor dead reckoning. So as most of you know, quadrotors are used for a variety of applications like deliveries, surveillance, and the list goes on. Usually, there are 2 types of environment a quadrotor operates in: outdoor environment and an indoor environment. On the outdoor environment, usually the quadrotor relies on GNSS signals. In the indoor environment, usually we rely on a camera. In both approaches, we use together with the camera or the GNSS, we use also inertial sensors. In theory, the camera and GNSS supposed to work all the time, but in practice, we have a lot of limitations. For example, if we are a quadrotor making a delivery and we are arriving to an urban environment, then the buildings will block the view to the satellites or will cause a multipass in the signals, which will greatly degrade the performance. In indoor environments, sometimes there is lighting conditions, camera obstructions that does not enable the camera to work properly. In both situations, the Quadrotor navigation solution will rely only on the inertial sensors. And as I mentioned before, those contain biases and noise, and when integrated, they cause the navigation solution to drift. So this is an undesired situation. So what we suggested first in a model-based approach called QDR, Quadrotor Dead Reckoning, is instead of flying the Quadrotor in a straight line, which mostly the Quadrotors fly in a straight line, is to give the Quadrotor a periodic motion, as you can see here in this example. And when we are giving the Quadrotor this periodic example, motion, we cause the motion to be nonlinear, and it helps us to extract features and let them work better with networks. So this is our first approach. We show that using a model-based approach to estimate the peak-to-peak distance, as we did in pedestrian net reckoning, we are able to get very nice result and bond the INS drift. And later on, we proposed a QuadNet. QuadNet is an end-to-end network, as similar to those I showed you in the PDR. We use only the accelerometers and gyroscope readings, plug them into a network to regress the change in distance and height. In PDR, we regress only the distance, but now in the Quadrotor, we have also the vertical dimension, which is important. So we want to estimate also the Quadrotor height relative to the ground. And as we always do, we try two types of architectures. One is a CNN architecture, and the other is a long short-term memory architecture. And you can see here the results. Those results are from a real data set recording by the Matrice 300. And you can see here both train and test. You can see here in the upper figure is the distance error, and the lower one is the height error, and the green is the INS solution. Assuming that we are flying in a straight line, you can see it diverge quite rapidly compared to our approaches. In the red, you can see the QDR, the model-based approach, and in those two represent our deep learning solutions. And you can see here that there is also a drift in this solution because, again, we're with inertial sensors, but the rate of the drift is much smaller than the INS. Of course, this is only available for short-time situations when we don't have GNSS or the camera is not available. But in those situations, we managed to greatly improve the performance. Currently, we are working also on smaller Quadrotors to verify that our approach is working for small Quadrotors that fly indoors. Okay, so we talk a lot about artificial intelligence, but it's nice to remember that guidance is the highest form of intelligence, regardless of artificial intelligence. And I also want to mention that our team is growing, and we are looking for a graduate or postdoctoral research fellows, and we'll be happy to conduct collaboration with industry and academia. And I thank you very much for your time being here. And if you have questions, I'll be happy to answer. Thank you.
So thank you very much, Itzik, for being here today and for giving us this interesting talk. So everybody, if you have questions, please type them in the chat. We will read the questions here and are happy to answer, or not me, but Itzik will answer them. So please feel free and involve with us here. So otherwise, if everything is clear, we are also happy, then maybe I just will ask a question, Itzik. So how are your involvements here with German scientists? Do you have already any kind of collaborations or are interested to work with? Or this would be something what I was really interested in. You said you were at a conference here in Germany as well. So
yeah, well, actually, as I mentioned, I'm quite new in the academia. I'm working in the industry a lot, so my lab is 3 years old. So I'm building the connection, and I hope to build a connection with German scientists and researchers. Yeah, I'm looking forward to that.
Cool. So maybe later on you can also share your contact information with us. So in case our participants are interested in asking maybe more individual questions or getting in touch with you, then you're also available.
Yes, of course.
Assume via your
send me an email.
Exactly. Cool. So then I would also thank you, everybody here taking part virtually with us. I wish you all a very nice day and weekend. And yeah, let's keep in touch and be involved with our HIDA lectures in the future. So goodbye, everyone, and have a very nice day.
Bye. Thank you.